Good afternoon, everybody. Before we start, I would like also to acknowledge the work of three colleagues that helped prepare the material, John Luciano and Steve Schaef. They both work with me in Master Builders, as well as Sean Rankman, who is a student on the CIM program at the New Jersey Institute of Technology. So let's start by why this is an important topic and why it deserves some full attention. Returned concrete has been a problem in our industry for many years, and this issue continues to grow. As an example, with the increased cost in labor, many contractors today do overorder concrete because it's cheaper to them to return a fraction of that concrete than to pay for idle teams or pauses in the job site. This causes concrete to be returned. NRMCA estimates that according to the NRMCA and to the industry, the return concrete volume is anywhere between 2 and 10% of the produced volume by certain producers. That amount varies, of course, by region and by the applications that the producers are supplying the concrete to. Also, return concrete is an operational, a financial, and an environmental burden or challenge for many concrete producers. Imagine ready-mix sites that are in urban areas where space available to treat or to dispose of concrete is at a premium. So it's not uncommon to see producers mounting returned concrete at their site and either crushing it themselves or sending it off-site to be crushed at a later stage. This material then can be used either as a road base, backfill, or again as aggregates, as we just saw Professor Cavalim speaking. However, crushing concrete is pretty energy intensive. It is not very cheap, and dealing with chunks of concrete of various sizes and weights can be potentially dangerous. And again, depending on where the ready-mix sites are located, piles of returned concrete, they take up space, and that space comes at a premium. And also can be an eyesore not only for the producer, but for the neighborhoods in which the ready-mix plants are inserted in. So let's look at a few options that producers have today to deal with the returned concrete. Being from an admixture company, I have to add a disclaimer here. I'm not going to talk about hydration control of returned concrete, which is with, for example, stabilizers that you can then later batch fresh concrete on top of it and sell it in other non-critical applications. That is not the scope. The scope really is what to do with the concrete after it's returned, considering that you cannot stabilize it. So the first option, very clear, just send it to a reclaimer. That comes at some cost. It can be either on the site or off-site. It has costs associated with energy, with water, with transportation of the materials. Another option is the famous out of sight, out of mind. Just pay to dump it elsewhere. And this is very common. However, the costs associated with transporting the materials to the off-site dumping area, as well as the fees that are charged by those locations, are significant. Then we have another option, what to do with returned concrete. Producing blocks and selling them. Many ready-mix producers do it. It is actually a pretty lucrative alternative. However, it requires space. It requires labor to put the formwork together and prepare the formwork. It requires labor to pour in the mold and then demold. and you need surface area to be able to stockpile those blocks. And by the way, someone has to sell it. So you need also some level of infrastructure to sell those blocks. Another option, and it's what I'm going to cover a little bit more in depth today here, is to transform the still plastic returned concrete instantly into aggregates by using admixtures that enable granularization of that. Those aggregates, or the RCA that comes out of it, just like regular RCA, can be used as backfill, as road base, but also to make concrete. And we'll see a little bit more of that. Last but not least, the traditional breaking and stockpiling, either mechanical crushing the concrete and then selling it or reusing it, as well as just hauling it off-site. So let's go and talk a little bit more about this technology, about how to transform plastic concrete into recycled aggregates. The technology consists of 3 different steps. First, when the returned concrete gets back on site, the total volume of returned concrete inside the truck needs to be estimated or determined. Then bags of this particular admixture are added to the truck, and the drum has to be mixed for about 2 minutes. This is a very fast-acting polymer that's in there, and in a matter usually of 60 seconds to, let's say, 90 seconds, you can already hear the different sound inside the concrete truck, from the traditional swooshing of more plastic concrete and to the rattling of the aggregates being formed. After these 2 minutes mixing, the concrete is then discharged in piles, and in the next day, just with a traditional front loader, they come and they put it into the aggregate piles or on the stockpiles they have separated for that. So why don't we look at an example of this technology on a mortar, on a very fluid mortar. The admixture is then added, as you can see here. The admixture is a super absorbent polymer, but of a special kind, not necessarily the super absorbent polymer you will find in baby diapers or in other hygiene products. When added to the concrete, it reacts partly because also of the high alkalinity of the mix, and it draws all the water out of the system, and basically this is how you start forming dry aggregate in a matter of seconds. As you can see here, we only lapsed around 40 seconds, and something that was liquid as a grout is no longer workable. Yeah, in a lab with a pedal mixer, that's simple. Why don't we look also in real life? So here we have an example of the same material being added to concrete. And after 2 minutes of mixing, you can just discharge the truck. This was 8-inch concrete that was treated. After 2 minutes, this is how it looks like. You can see the individual aggregates coming out of the chute. The next morning, the front loader can come and it moves, it behaves, it acts just like common coarse aggregate. So one of the main things, of course, as we just saw in the previous presentation, we need to characterize the material, and that is essential. What we're talking about here is basically an aggregate that is coated with a thin layer of combination of hydrated and unhydrated cementitious materials. The density is slightly lower than the virgin coarse aggregate would be, considering that it has also a little bit of sand, water, and of course the cementitious material. In the example that I will give next, The virgin limestone, for example, had a specific gravity of 2.8, and the reclaimed material that we made using that aggregate ended up with a specific gravity just over 2.6. And of course, the gradation has also to be determined, and the gradation will vary according to the initial materials that you had in the concrete, as well as the type of mixture and the volume that was inside the concrete truck, mainly because of shear forces, and the post-handling equipment, for example, the front loader type that you will use to stockpile the material. So having those aggregates in hand, we ran several concrete trials in our laboratories back in Beechwood, and I will show compilation of data of some of those, or at least in one of those cases. Here the virgin, or the reference mix, had a cement factor of 611 pounds per yard. The water cement ratio was set at 0.42. The mix had a coarse aggregate volume of 37%, and we did air and train the mix. So we were shooting for about 5.5% air, so we got somewhere in there. This concrete mix was then treated with the admixture and the aggregates generated. And through the following days, we did several new concrete mixes by replacing the coarse aggregate volume of that reference mix with anywhere between 10, 20, 30% of the recycled aggregate. In terms of workability, what we can see is that workability ends up being basically the same. In some cases, in some mixes, what we saw was a very, very slight increase in the water reducer demand, but in most cases, it was not noticeable. So here you can see that. When we go into the strengths, what we see is also the same thing. The strengths of the reference, as well as with 10, 20, 30% replacement of the coarse aggregate with the RCA, they are very comparable in all cases. So, conclusion is that concrete produced with this type of RCA exhibits similar workability and compressive strength relative to the reference. But one of the questions that our customers were also asking is, okay, I understand that that slump doesn't vary much, and for that we can also always add a little bit more water reducer or water, and we see that the strengths are pretty decent. And one of the characteristics is that by not having to go through the fracturing or the crushing process, those aggregates tend to behave in a little different manner. But that's not all of it. Durability is also a very important aspect of concrete. So we ran a few durability studies as well. Compiling all the data from the different mix designs, what we can see is that in terms of length change, when tested according to 157, ESTM 157, length change is also very comparable. The concrete behaves basically the same. In terms of freeze and thaw durability, when tested according to ASTM C666, this case is method A, the relative dynamic modulus also does not vary. Very comparable results. Also very important, especially in the colder climates, is scaling. Here we used the Canadian test method, which evaluates not only the surface appearance of the concrete after going through 50 cycles of freezing and thawing with de-icing salts, but it also measures mass loss. And the ratings, so the visual rating of the concrete, the aspect of the concrete is the same, and the mass loss also very comparable. We are now running different types of durability tests as well. Still a little bit too early, but data on RCP, rapid chloride permeability, is also comparable. Data related to sorptivity, also very comparable, and we're doing more. With that, what we want to ensure is that transforming the plastic return concrete into aggregates that can thereafter be used to make new concrete is an alternative that is viable in some cases and should be studied. So let's look a little bit at opportunities, and we will quantify them a little bit in the coming slides as well. So utilizing treated material as aggregate replacement, you have material savings at the plant, ranging anywhere between $10 and $15 per ton average. It will vary a lot depending on where in the country you are or where in the world you are. However, it requires material qualification, so you need to know how the aggregates that you just generated look like. There are some limits in application and usage where you're going to use that concrete. You have to do the durability testing, you have to do the mechanical properties testing to ensure that the concrete will be usable. It requires some level of operational change. You will have to treat the returned concrete and generate it. You will have to move the aggregates that you generated into a stockpile, and you will be able to choose when to use and when not to use that aggregate according to the applications that you're selling the concrete to. There is always the option on selling that material for road base or backfill. However, that would translate, just like by making the blocks, you would need some form of sale person inside the ready-mix operation to be able to sell that material. And in some locations, there might be issues with clean fill testing. So the material would have to be tested to ensure that when used as road base or backfill, wouldn't cause any contamination on the subsoil. We know that that would not be the case, but nevertheless, some locations require that testing. And looking also at the producers, it brings savings in terms of that the treated material is easier to handle than big concrete chunks that were dumped on the site. And in case of disposal applications, it's easier to transport and load. Another characteristic that we also saw is that when granularizing the concrete inside the truck, the effect of the rocks that are being formed or the aggregate being formed inside the truck helps clean the fins and keeps the truck in better condition as well. So looking at those possibilities, there was a group inside the NRMCA, inside the Developing Industry Leaders program, that created a tool that helps ready-mix producers to quantify the benefits, the pros, and also the cons of different ways of treating returned concrete. One of the ways that is part of the tool is the traditional dumping off-site. There, the tool considers inputs such as the wages of the drivers, the time to travel to the dumping site, the fees associated with disposal, and then the time to wash the truck afterwards. The tool also takes in consideration manufacturing the concrete blocks. Usually those are 0.6 cubic yard blocks that have the two hooks on the top. The variables that are also taken in account in this model are the wages associated with the driver, the time to discharge and then wash the truck, the costs of hook, the time to demold, stack, and load, and also to make the form or to put the formwork together again, as well as the profits that the producers will have by selling that material. Reclaiming concrete, the inputs are, again, wages for the drivers, time for truck washing, the operators or the loading operator wages, the times involved in stockpiling all the materials, the equipment, as well as profit in case of reuse or sale. For the granularized admixtures, about the same, including the cost of admixture and the wages and the times. Same for mechanical crushing, and same for hauling off-site. The tool will be available to the producers that are members of the NRMCA before the end of the year. And this is how it looks like. So basically, it will correlate for a given volume of concrete that's returned to the site every year, it will correlate the total costs involved. If there is any revenue associated, for example, in the case of selling the blocks, that's why it's very profitable, if you have the means to do it. And it breaks down to the net revenue cost per cubic yard. So this is what I wanted to share with you today, and I'm happy to entertain any questions if you have.